Just a few practical considerations that you'll maybe come up with when you start using these sorts of models. The variance components, as I said, they're only going to be positive if there's more variation than expected by chance due to a random effect. So if you say fit had animals from different farms and you fitted farms, you'd only get a positive variance component for farms if there was more variation than you would expect by chance. Sometimes that gives rise to negative variance components. The estimation methods sometimes will allow those estimates to go negative, but you can't really allow that because we've made the assumption that the random effects have got normal distributions and you can't have negative values of variances, so that's not permissible. And quite often the negative estimates are just an underestimate of the true variance component, and you'll have more chance of getting them if the true variance component is actually very small, if you've got a small number of random effect categories, so for example a small number of biological replicates, or a small number of observations per random effect category, so that would be maybe a small number of technical replicates. So in the example I showed earlier, probably would be a reasonable chance of getting a negative variance component just by chance if the true underlying amount of variability was small. So what do you do in that situation? Well, the usual thing that's done is you say, well, in the assumptions I made about this model, I can't believe that there's negative variance here, there's less variance than expected by chance. So we'll fix the variance component at 0. And in fact, most packages do this by default. Most of the packages I've come across will do this by default, but will optionally allow you to have a negative variance component if you want to, but you have to bear in mind that's not really permitted given the model you've set up. You could alternatively say, well, there's no variance here, I'll take this random effect out of the model altogether. That will lead to exactly the same results. The only thing that will differ is the degrees of freedom for the significance tests, so you might sometimes want to do that. And very occasionally, a negative variance component is an indication of negative correlation within the random effects. And I never saw, when I worked in medicine, I never saw any examples of when that would be feasible at all, but perhaps you could imagine in sort of an animal trial it might be a possibility if you, for example, were doing an animal experiment where you saw how much you're feeding animals and you wanted to see how much they weighed, different diets, and animals were grouped in cages. You might imagine there'd be quite a lot of variability in how much animals ate and weighed within a cage. You might have greedier animals than others that got most of the food. And so there might actually be more variation within the cages than between them. And if you fitted cage effects as random, that would then lead to a negative variance component for cages. But we said that's not allowed. So just to sort of draw attention to the fact, you could redefine the model if you wanted to. You could take out those random cage effects and say, well, I'm going to just model the error term and allow negative correlation between the animals in the same cage. And so instead of having a random effect, we just have this multivariate normal distribution for our error terms, and just to try and bring that to life a bit. If we fitted cage effects as random, and here, say we've got 4 animals in the first cage, 2 in the second cage, 3 in the third cage, then this is what that R matrix here would look like. It's a correlation, well, a covariance matrix, and it would look something like this. So we've got the cage variance component plus the residual variance down the diagonal of the matrix, which is the overall variability between the animals. And this is the covariance between animals in the same cage, which is sigma c squared. And that's here, it's a variance component. And we're saying, well, that variance component might be negative, but it shouldn't, that's not allowed because it's a variance component. But what we can do, if we redefine that matrix in terms of correlations, we can redefine it like this. So instead of variance components from the random effects, we've just got one residual variance, and we've got a correlation parameter for the correlation between animals in the same cage. And of course, correlations are allowed to be negative as well as positive, so we've now got a model that is effectively allowing for a negative variance component for cages, but we've defined it in terms of correlations between animals in the same cage. And yeah, all these zeros are still there. They're saying there's no correlation between animals that are in different cages. You will quite often find in your analyses that you get variance components of 0, and that's why it's because it's trying to estimate something negative, but it's fixed it at 0, so it's nothing to worry about unless you think there is actually negative correlation.